We have valence bond theory to explain the type of bonding in case of the coordination complex, according to which here the central metal atom in any complex is going to provide the number of vacant sp_d orbitals. So metal accepts the pair of electron here, and the ligand is going to donate electron pairs. So the metal should have vacant orbitals to accept the electron pairs. So this is going to provide either s or p or d orbitals for ligands. That's how it is going to form the coordinate bond. So the number of vacant orbitals provided by the central metal atom is equal to its coordination number. Say it is going to provide es np3 orbitals. These are the orbitals of the central metal atom. So the coordination number is equal to 4 here, because it is going to, the metal atom is going to provide 4 orbitals, and each ligand is going to give 4 pair of electron now. So this hybridization now is called as sp3, and there are 4 orbitals before they undergo hybridization, and after hybridization you are going to get 4 sp3 hybrid orbitals, and each of them are filled by the electrons given by the ligands. So vacant orbitals of central metal ion overlaps with the filled orbitals of the ligand to form the coordinate bond, and the vacant orbitals undergo hybridization to form the same number of hybrid orbitals. So before hybridization there are 3p and s orbitals were involved. Now you have 4 sp3 hybrid orbitals, and geometry depends on this hybridization. If it is sp3 then it's tetrahedral, if it is a dsp2 then it's square planar, if it is a sp3d2 or d2sp3 then it's octahedral. And then we have, in case of hybridization, say you have something called as 3d orbitals, 4s orbital, 4p orbital and 4e orbital. So in case during the hybridization, if the 3d orbitals are used, that's the inner orbitals are used, that's n minus 1d, this is ns, this is np and this is nd, then this becomes n minus 1d, where n is this number. So if it 4s is ns, 3 is n minus 1d. So in this case, where the inner orbitals are used, then it is called as inner orbital complex. If the 4d, which is the outermost, is used, then it is called as outer orbital complex. So once you do the hybridization, if there is any unpaired electron left, then it is going to show the paramagnetic nature, which is going to be attracted by the magnetic field. If there is no unpaired electron or all the electrons are paired up, then the complex would be diamagnetic. We are going to study the VBT in case of some complexes. The first complex which we are going to take here is nickel tetracarbonyl. It's a homoleptic complex with the nickel as the central metal atom and the carbonyl as a ligand. So carbonyl is a monodentate ligand which is going to donate a pair of electron through one donor atom, and it can donate just one pair of electron. So the 4 carbonyl are going to donate 4 pairs of electron to the central metal atom, and also the carbonyl is regarded as the strong ligand. A ligand which is strong has capacity to pair up the unpaired electrons of the central metal atom. So the outermost electronic outermost orbitals are here. So for nickel the atomic number is 28, so the configuration would be 3d84s2. We have written only the outermost shell, and you can see there are 2 unpaired electrons. When the carbonyl is going to approach, these electrons try to pair up. So the electron jumping starts and the electrons are paired up. Now this orbital is empty, this one orbital and these 3 orbitals. So together sp3, 4 sp3 hybrid orbitals are formed here, and these hybrid orbitals are filled with the electrons which are given by the ligand carbonyl. So you can see them in different colors, and the hybridization is sp3, and you can see the molecule has a tetrahedral shape, tetrahedral geometry. And also if you see in the orbital diagram or this orbital structure, you don't see any unpaired electron. Unpaired electrons are not there, so this is regarded as diamagnetic. We are going to consider one more complex, that's nickel tetracyanide, that's NiCN42 minus. So in case of NiCN42 minus, again the cyanide is a strong ligand and it is monodentate. It is going to donate the pair of electron through one donor atom, monodentate and strong. And the cyanide carries a -1 charge. So if you calculate the charge on nickel, it comes out as +2. So the configuration is 3D84S0 once again. But here, this is empty because nickel is in +2 state, whereas here the nickel was in 0 state. You have to remember this. Here nickel was in the 0 oxidation state, as carbonyl is a neutral ligand. Here nickel is in +2 oxidation state, so 2 electrons are not there. When the strong ligand approaches, this electron is going to jump here and the electrons are paired. So now this orbital is free, that's D, and 1s and 2p orbitals are going to hybridize and they are going to form 4 dsp2 hybrid orbitals. And each cyanide is going to donate one pair of electrons. So these orbitals are occupied by the electrons given by cyanide. And due to change in the hybridization, you have the square planar structure, square planar geometry, and the hybridization is dsp2. Again, if you see this, there is no unpaired electron, then it would be diamagnetic. If you consider one more complex, that's NiCl42 minus, tetrachloronickelate 2. In this particular complex, the halogens are regarded as weak ligands. The electron pairing here won't take place. As a result, you will have the structure like this. These are the d orbitals, that's 3 d orbitals of nickel. Here nickel carries 2 plus charge, so the configuration would be 3d8, 4s0, 4p0. Now the electrons are filled here, 8 electrons. You have to give 1 electron each, then pair them up. Now, being a weak ligand, it can't pair up the electrons here, and these electrons are retained, and then these orbitals are occupied by the electrons given by 4 chlorine ions. So because of this, this undergoes sp3 hybridization and the molecule has the tetrahedral shape, but here there are unpaired electrons. Due to the presence of the unpaired electron, it becomes paramagnetic in nature. So we have seen the coordination number 4 complexes where there are 4 ligands which are present, and you can have two types of hybridization. One is the sp3, because of which the molecule will be tetrahedral, and if you have the dsp2 hybridization, then the molecule will have the square planar shape. And in both the cases, if you have unpaired electrons present, then the molecule or the complex is regarded as paramagnetic. If there is no unpaired electron, then the molecule or the complex is regarded as diamagnetic. And we have the complexes of coordination number 6. So there will be 6 ligands. And the first complex which we are going to study is hexammine cobalt 3. Here, cobalt is a central metal atom and ammonia is a neutral ligand, and it's relatively strong and it's unidentate also. And the charge, since the charge on ammonia is 0, the charge on the cobalt would be 3 plus. So the configuration of cobalt, atomic number is 27. So the configuration is 3d7, 4s2. When it is in the +3 state, 2 electrons from here and 1 electron from here are gone. So the configuration becomes 3d6, 4s0, 4p0. Now here, when the ligand is approaching, that's NH3, it is going to pair up the electron. As a result, these electrons are going to jump here. And you have this many orbitals here, and there are 6 ligands, so 6 pair of electrons are given. So you need 6 boxes empty, 1, 2, 3, 4, 5, 6. So these are the d orbitals, this is the s orbital, these 3 are the p orbitals. So these are going to hybridize to form d2sp3 hybrid orbitals. And these are occupied by the electron pairs which are given by the ligand ammonia. And here you can see there is no unpaired electron, so the complex will be diamagnetic. And here the d which is involved is 3d, then 4s and 4p, these are the orbitals which are going to hybridize. And if this is the ens orbital, that's 4 is n, then 3 will be n minus 1 d. So the inner d orbitals are involved here, so this is called as inner orbital complex. So if the hybridization is d to sp3, you can see the structure is octahedral. We have one more complex of cobalt, hexafluoridocobaltate 3. Here fluoride is a unidentate ligand and it is a negative ligand. So the charge is -1. If you calculate the charge on cobalt, it will come out as 3 plus. The configuration will be 3d6 in case of a 3 plus configuration. And here the ligand, that's a halogen, is considered as weak ligand, because of which it can't pair up the electrons here. And you need 6 orbitals for metal, because each fluorine is going to donate one pair of electrons. So one orbital, 2, 3, 4, and you need 2 more. So those are taken from the 4d orbitals. So totally 6 orbitals are going to hybridize and form sp3d2 hybrid orbitals, and they are occupied by the electron pairs which are given by the ligands, which is shown in blue color. And again the molecule which has sp3d2 hybridization, the shape will be octahedral itself, but you can see the number of unpaired electrons inside. So this is called, this is regarded as paramagnetic complex. And also if you see this, Nd orbitals are involved, 4s, 4p and 4d. If this is Ns, this is Np and this is Nd. So outer d orbitals are involved. This is called as outer orbital complex. So in case of coordination number 6 and 4, you have to see the type of ligand first. If the ligand is strong, then it is going to pair up the electron. If the ligand is weak, then it can't pair up the electron. And the magnetic property depends on the number of unpaired electrons. If there are unpaired electrons, then the complex is paramagnetic, otherwise it is diamagnetic. And depending on the hybridization, in case of octahedral complexes, that's coordination number is equal to 6, whether you have D2sp3 hybridization or you have sp3d2 hybridization, the complex would be octahedral in shape.